You know that feeling when you just like sweep all your messy, tangled charging cables and loose papers into a single desk drawer?
Oh, yeah. And then you proudly call your workspace decluttered.
Right, exactly. But you haven't actually removed the mess, of course. You've just
Hmm.
traded this visible, understandable clutter for, well, an invisible headache.
A headache that is absolutely going to hit you the second you actually need to find a specific cable.
Exactly. And today we are looking at a code base that did exactly that. Welcome to the deep dive.
Yeah, we have a pretty brilliant case study today on the hidden costs of writing elegant code.
We do. So we are pulling from a developer diary entry published today, July 20, 2026, by a programmer named Ang.
All right.
And the entry is titled Notes on Haskell-Programming Part 191. Combine year-to-Chinese and year-to-Chinese formal into one function.
It's a very specific title.
Very. And our mission here is to unpack a specific, universally relatable tension in software development.
Which is the collision between the dogmatic pursuit of the DRY principle, don't repeat yourself, and the actual reality of human cognitive load.
Yes. We are going to look at what Ang gained by squashing two functions together, and surprisingly, the invisible traps that were set in the exact same process.
It's a perfect microcosm of everyday software architecture. I mean, on the surface, Ang is doing what every senior developer mentors their juniors to do, right?
Hunt down redundancy and just destroy it.
Right. But the ripple effects of that optimization really highlight why programming is as much about human psychology as it is about machine logic.
Okay, let's unpack this. We need to examine the before state of Ang's code base.
Yeah, let's set the stage.
So Ang is writing in Haskell, which is a purely functional programming language, and they've built out two distinct functions to handle a very specific string manipulation task.
And the goal here is to take a standard Gregorian year integer, like the year 2026, and convert it into Chinese numeral text.
Right. And the initial approach here is wonderfully explicit. Like there are two separate paths for two separate use cases.
Yeah, so function one is called yearToChinese.
Right.
You pass it the integer 2026, and it returns the simplified regular Chinese digits.
And visually, if you look at the text output in Ang's notes, it's represented by four standard characters. They look like horizontal lines and relatively simple strokes.
Right. It is the everyday conversational way to write the year.
But then we have function 2 sitting right below it in the code labeled year-to-Chinese formal.
Right.
You pass it the exact same integer, 2026, but the output is entirely different. It generates formal digits, which are incredibly dense and visually complex.
And Ang's notes explicitly mention that this formal version is mandated for financial purposes, which is, a fascinating piece of domain logic to just stumble across in a code base.
It really is. And I mean, why is that distinction so important?
Well, understanding the why behind that domain logic is crucial. In Chinese culture, the simple everyday numerals, like the character for 1, which is just a single horizontal line, or 2, which is 2 lines, they are highly susceptible to forgery.
Oh, wow. Yeah, I guess you could just add a stroke.
Exactly. If you're writing a bank draft or a legal contract, a bad actor can alter those numbers with a single quick stroke of a pen. So to prevent this, financial systems use these formal characters.
Because they're just way too intricate to be subtly modified.
Right. They're intricate enough that they cannot be subtly modified into another number. They essentially provide security through typographical complexity.
That makes perfect sense. The application fundamentally needs both versions to exist. But looking at the code base in this before state, you can immediately sense the developer's itch, right?
Oh, for sure. You have these two functions side by side executing almost the exact same logic.
Yeah, just pulling from different output pools. It is literally like walking into a commercial kitchen and seeing two massive, identical industrial espresso machines taking up all this counter space. And one is wired exclusively to brew regular coffee, and the other is wired exactly the same, but exclusively for decaf.
It takes up a lot of visual space, even if the operational logic is completely flawless.
Exactly the kind of thing that drives a functional programmer crazy. I mean, you look at those machines and think, well, these share 99% of the same internal parts. Why don't I just build one machine with a toggle switch on the front?
And that desire to consolidate is the driving force behind Ang's refactor. The instinct is completely rational.
Right, because code duplication is basically a sin in software engineering.
Yeah, it's often seen as a total liability. If you have a bug in the shared logic, you have to remember to fix it in two places. If the requirements change, you have to update two separate functions.
So Ang decides to dismantle the dual setup. Here's where it gets really interesting. Ang tears down the two functions, and builds a single, unified yearToChinese function.
Right.
And to make that toggle switch work, they introduce a new argument to the function signature, a Boolean, true or false, called isFormal.
And this is where we need to look closely at the Haskell mechanics Ang deployed. Haskell is known for its concise mathematical syntax.
Yeah.
What's fascinating here is the specific Haskell mechanism Ang used to handle this Boolean logic. It's a feature called a guard.
Visually, the guard is represented in the code by the pipe symbol, right? That straight vertical line.
Exactly. Think of the guard as a traffic controller inside the function. So Ang created a local helper function called yearToChinese.
Okay.
The job of this helper is to take a single integer digit, say a 2, and look it up in a mapping dictionary called yearToChinese map.
And this map holds a series of tuples, right? Like packages of 3 value.
Correct. Each tuple in the map contains the integer digit, which is D, the regular character R, and the formal character F.
So when the helper function grabs the tuple for the number 2, it holds all the possible translations in its hands at once.
Exactly. And now the guard steps in to evaluate the Boolean state.
Right, so let's walk through that logic. The code looks up a digit in that map. How does the pattern matching handle the extraction?
Well, the first line of the guard checks the toggle. If isFormal evaluates to true, it pattern matches the tuple to extract the third element.
The F, the formal character.
Yes, it essentially ignores the regular character entirely.
But if isFormal is false, it just falls through to the next condition, right?
Yeah, it hits the otherwise condition. Ang uses the standard otherwise keyword, which acts as the default fallback.
Right.
When it hits otherwise, which is a default or simplified case, it reaches into the tuple and extracts the second element, the R, the regular character.
It's undeniably elegant. I mean, the internal logic is clean, the duplication is gone, and you can see in Ang's notes that the refactor was a success.
Yeah, the outputs match.
Yeah, in the comments detailing the after state, the formal output for 2026 is documented as show. So the final character for the number 6 has actually shifted to its highly complex formal counterpart.
Proving that the new lookup machinery is pulling the correct values from the tuples.
Right. So the 2 giant coffee machines are gone. We now have one sleek, unified function. And by the strict definition of the DRY principle, Ang has achieved total victory.
Total victory on paper. Sure.
Yeah, I have to step in here and push back on that idea of victory, because when you look beyond the function definition and look at the caller code, this feels like a massive step backward.
It does. And Ang actually highlights this immediate tension in the diary entry itself. The implementation is clean, but the integration is messy.
Very messy. So what does this all mean? Let's look at the caller code, the actual places in the broader system where another developer has to invoke this function.
Right, the person actually using the code.
Yeah. To get the standard everyday Chinese year, the caller code now looks like this. yearToChinese false 2026.
yearToChinese false 2026.
yearToChinese false 2026. I mean, put yourself in the shoes of a maintainer reading that line of code 6 months from now. You are scanning through hundreds of lines of logic, trying to track down a bug, and you hit yearToChinese false.
What does false mean in that context?
Exactly. Are we saying it's not a Chinese year? Are we instructing the system to abort the translation?
It introduces immediate ambiguity.
Yes. Without breaking your flow state, opening up a new window, navigating to the file where the function is defined, and reading the internal guard logic. The word false is completely meaningless.
Yeah.
Ang saved a few lines of code in the definition file, but basically outsourced a massive cognitive burden to every single person who ever has to read the caller code.
If we connect this to the bigger picture, what you are describing is a classic pervasive anti-pattern in software architecture.
Oh, really?
Yeah, it's known as the magic Boolean.
A magic Boolean. It's a great term. I mean, it sounds like a feature, but it operates exactly like a trap.
Yeah, it really does. A magic Boolean occurs anytime you pass a primitive true or false value into a function. And the semantic meaning of that true or false cannot be deduced solely from the function signature at the call site.
Right, because false doesn't inherently mean regular.
Exactly. When the code base had yearToChinese formal, the function was entirely self-documenting. You didn't need to look under the hood to know what it produced. The name was the documentation.
And developers fall into this trap constantly, don't they? The allure of stripping out redundant lines of code is so strong that we forget code is read 10 times more often than it is actually written.
We do. And honestly, this stems from a fundamental misunderstanding of what the DRY principle actually means.
How so?
Well, don't repeat yourself was originally coined to prevent the duplication of knowledge or business logic within a system. But over time, it mutated into this dogmatic crusade against duplicating text.
Ah, so Aang saw textual redundancy. The two functions looked visually similar and rushed to compress them.
Yes, but in doing so, they sacrificed the semantic clarity of the original code.
No, wait, if they really wanted to consolidate without falling into the magic Boolean trap, they could have used a custom type, right? Like, instead of passing a primitive Boolean, pass an enum.
That would be the preferred architectural pattern, yes. In Haskell, it is incredibly easy to define a custom algebraic data type.
Right.
You could define a type called format with two states, regular and formal. Then the caller code becomes yearToChinese regular 2026.
yearToChinese regular 2026? Wow, that immediately solves the readability problem.
It really does. It gives you the single function definition without destroying the self-documenting nature of the caller code.
Right.
But, developers often reach for the Boolean because it's a built-in primitive.
It's just sitting right there.
Yeah. It feels faster in the moment. It saves a few keystrokes today at the massive expense of readability tomorrow.
It brings us right back to that decluttered desk drawer analogy. You shoved everything into one place to make the surface look pristine, but the daily operation of finding what you need is actually worse.
Much worse.
But what is truly brilliant about this developer diary is that Aang doesn't just stop at recognizing the readability problem. They end the entry with a phenomenal cliffhanger.
Oh, the hidden flaw.
Yes. Aang writes, and I quote, "However, can you spot a significant performance and redundant codes in our changes? More on this in future post."
Which is such a good tease.
Right. They challenge the reader to look closely at the new unified architecture.
This raises an important question. We have the after code block in front of us. We need to evaluate the structural topology of this function and deduce what Aang actually meant.
Where is the performance penalty hiding in this supposedly optimized code?
Let's trace the execution path. The main function receives the integer 2026. The very first thing it does is use the Haskell show function.
Right, and show is a type class method that converts values into strings, if I remember correctly.
You got it. So it takes the integer 2026 and turns it into a string. And in Haskell, a string is simply a list of characters. So we now have a list containing 2, 0, 2, and 6.
Okay, so we have a list of 4 separate characters. Next, Aang uses the map function to apply our helper, yearToChinese, over that entire list.
Right, and think about how map operates fundamentally. It iterates, it takes a function, and applies it to every single element in a collection, one by one.
Wait, hang on. If map is iterating over every character in the string, and it is applying the yearToChinese helper function, where exactly is the Boolean guard located?
The Boolean guard, the logic that checks if his formal is true or false, is nested inside the yearToChinese helper function.
It's inside the map function, so it isn't evaluating the Boolean toggle just once for the whole year.
Nope. Let's walk through the loop.
Okay, it grabs the first character, the 2. It dives into the helper function. The guard wakes up and asks, is formal true or false?
Right.
Checks the state, grabs the appropriate character from the tuple, and returns it.
Then the map function moves to the second character, the 0.
It dives into the helper function again. The guard wakes up again and asks the exact same question. Is formal true or false?
And it does this for the 2 and then again for the 6.
It evaluates the conditional logic 4 separate times. And the Boolean value hasn't even changed. It was passed into the main function once at the very beginning.
You've isolated the exact performance redundancy Aang was hinting at. This is a classic big O notation problem.
Yes.
What should have been an O of 1 operation, a constant time check where you evaluate the Boolean once at the top level, has been transformed into an O of N operation.
Because the condition is evaluated n times based on the length of the string.
Exactly.
I mean, think about the bouncer analogy. It's like hiring a bouncer for an exclusive VIP club, right?
Yep.
But instead of the bouncer checking your ID at the front door just once, they literally follow you inside the club.
Oh, that sounds awful.
Right. Every time you walk into a new room, like the lounge, the bar, the patio, the bouncer stops you and demands to check your ID all over again.
Wow, yeah.
You are the exact same person, your ID hasn't changed, but the verification process is running on an endless loop.
It is a profound waste of computational cycles. I mean, in a trivial example, like a 4-digit year, modern processors are fast enough that you will probably never notice the penalty.
Sure.
The compiler might even attempt to optimize it away under the hood. But architecture matters. Imagine if this function was designed to translate massive 100-digit financial figures in a high-frequency trading application.
Oh man, you would be forcing the processor to evaluate a static, unchanging Boolean flag hundreds of times per transaction, millions of times a second.
All Gagea because the developer wanted the code to look visually compact on their monitor. They nested the conditional check inside the iterative loop.
So to fix this, Ang really should have structured the Boolean check outside the map function.
Yes.
Like, check is formal at the front door. Are we doing formal or regular today? Make the decision once and then map the correct simplified translation logic over the string.
But notice what happens if you do that.
What do you mean?
If you pull the conditional logic up to the top level, you essentially have to write two separate pathways again. You end up recreating the structure of the two original coffee machines just under the umbrella of a single function name.
Oh, wow. You're right. The attempt to physically reduce the code actually created a performance redundancy logically. It's incredibly ironic.
And it perfectly encapsulates why senior engineers are often so wary of clever code. Visual brevity is not a reliable proxy for execution speed or maintainability.
So, wrapping up our journey through Ang's Part 191 notes, we have witnessed just a masterful display of the unintended consequences of refactoring.
We really have.
I mean, we started with two distinct functions, a setup that was undeniably repetitive, sure, but it featured crystalline logic and self-documenting color code.
Then, in service to the DRY principle, Ang introduced the toggle switch, the dreaded magic Boolean.
The code base got physically smaller, but the human readability absolutely plummeted. False became a mystery word, forcing every future developer to context switch and read the implementation details just to understand the API.
And beneath the surface of that readability damage, the structural placement of the Boolean guard inside the mapped helper function created a hidden performance drain.
Yeah, forcing the machine to endlessly ask a question it already knew the answer to. Refactoring code is clearly not just an exercise in making things shorter.
No, not at all.
It is a constant, unforgiving tightrope walk between machine efficiency, visual compactness, and human cognitive load. When you pull on one string to tighten the visual layout, you often introduce slack into the performance or the readability.
It is a zero-sum game of complexity. You can move the complexity around, but you rarely ever destroy it.
Which brings me to a final thought I want to leave you with today.
Okay, let's hear it.
Building on everything we've explored in this Haskell diary entry, what if the ultimate lesson here isn't actually about code at all? What if it's fundamentally about time displacement?
Time displacement. That's an interesting way to frame it.
Well, think about the core motivation behind creating a magic Boolean or throwing all your cables into one drawer. Whenever we abstract a process to save a few seconds for the person writing the system,
The condensing two explicit functions into one clever one.
right, we have to be intensely aware that we might be simultaneously stealing minutes or hours from the person reading the system later.
You are transferring the effort from the creator in the present to the maintainer in the future.
Yes. You are mortgaging the future to make today look a little bit cleaner. So, consider where in your own life you might be doing this.
Because it happens everywhere.
It really does. It doesn't have to be in a Haskell code base. Think about how you draft emails, how you set up your team's project management boards, or even just how you name your digital file.
Oh, file names are a big one.
Exactly. Where are you deploying your own version of a confusing false flag? A clever shortcut that makes perfect sense to you today while you are deep in the zone, but is practically guaranteed to baffle a colleague or even your future self tomorrow.
Are you actually removing the clutter, or are you just building a highly complex, visually appealing desk drawer?
Exactly. Because as Ang's developer diary proves, sometimes letting two distinct coffee machines take up space on the counter is actually the most elegant and considerate solution of all. Thanks for joining us on this deep dive. We'll catch you next time.